Today we are going to continue the review of thermodynamics by talking about the second law. And if we had time, we had enough time, we'll jump into the discussion on power cycles. Have you talked about power cycles in your thermodynamics? In your Can you give me some examples of famous power cycles? No, that's all right. We'll go over. Okay, so let's continue the discussion here first, and then we'll move on to the power cycle. Let's just make sure we are recording. Yes. Okay. So the first thing you want to do here. What happened? The first thing you want to do here is talk about properties evaluation. How can we evaluate properties? Evaluation of a material. We are mostly focused on pressure, volume, and temperature when evaluating the properties, as well as entropy and enthalpy, which I assume are properties that you already know about and you already have heard about, but we will talk about them anyways. The two more famous plots that we have is pressure, temperature, or PT plots, and also PV plots. There's also temperature, entropy plots, but we'll talk about those later. For example, for water, we have this type of plot, PT plot, right? Pretty sure you have seen this in your thermodynamics. All of these regions refer to a state of matter. Here we have liquid, here we have solid, and here we have gas, right? And a material can move from liquid to gas and gas to liquid with a process that's called evaporation or condensation. Also can move from solid to liquid or liquid to solid in a process that is called melting or solidification. But we can also go straight from solid to gas in a process called sublimation. What is this point here that connects all the three boundaries together? The solid liquid boundary, the gas liquid boundary, and solid gas boundary. What do we call this point? Critical point, exactly. And what is the importance of this point? What does it mean? What happens at this critical point? All phases of the substance can actually exist at that specific point. All phases exist. Okay. We actually can have a different perspective when looking at evaluating the properties of water. We can look at the pressure volume plots. A pressure volume plot usually looks like this. These lines here refer to the state lines. Really depends on your temperature. Becomes smaller. As you change the temperature, these lines move up between the regions, and this actually is called the triple line. Same is true for a different temperature, you get a different line, and so on and so forth. Something like this, a region like this. for temperatures smaller than critical temperature, you will always see this straight line. At the critical temperature, your line becomes like this, and as you go higher than critical temperature, your line goes outside of this region. Okay, so temperature is smaller than critical temperature, temperature equals to critical temperature, and temperature is larger than critical temperature. Okay. So these two type of graphs and the relationship between pressure and temperature is actually how we evaluate any material. We want to talk about two new properties here, which you have seen. I'm just going to put more emphasis on. One is the internal energy U, and this is just a review. I'll just go over this. If you had a question, please stop me and ask your questions, right? My assumption is that you have seen all of this before. You have like solved a lot of examples with them, and you just need the reminder. But if you don't know any of this, please ask, right? What is the internal energy? Internal energy is essentially, or is there anyone who can tell me what is the internal energy, like compared to kinetic energy and potential energy? Potential, right? Energy. Internal energy, it is obvious from its name. It is the energy that is contained within the system, right? So essentially the energy of molecules of the system, right? The bulk of the molecules, right? All of it together, right? But kinetic energy is of course different, and potential energy, we already have seen these before. But in most of our analysis, we just ignore kinetic and potential energy when it comes to psychoanalysis specifically, and we're going to see why later on. Okay. And the other topic we want to talk about, or we want to introduce, the other property we want to introduce is called enthalpy, which is a thermodynamic quantity equivalent to the total heat of the system, heat content of the system. These two play a very important role in any thermodynamic analysis. So far we have pressure, volume, temperature, internal energy, and also enthalpy. In the absence of kinetic energy and also the potential energy, internal enthalpy can be related to the internal energy plus the product of pressure and volume of the system. And if you recall from the previous lecture, this is the extensive representation of these properties. We can actually divide everything by mass and have the intensive representation of these properties, or per unit mass. Any questions so far? In order to evaluate these two properties, enthalpy and internal energy, and to find the relationships or to relate them to temperature, we actually have come up with the definitions of a specific heat capacities. That's constant volume, C of V, constant volume, a specific heat capacity. A specific heat, or heat capacity. Or constant pressure or isobaric, a specific heat. And these two are related to both pressure, to both temperature and internal energy, as well as the enthalpy or enthalpy, depending on the definition. So constant volume is defined as the derivative partial U partial T, the changes of internal energy with respect to changes in temperature when the volume is kept constant. And Cp is defined as partial pressure or changes in pressure with respect to temperature. Partial enthalpy with respect to temperature when pressure is kept constant. And these are properties of the matter. For example, air has its own specific heat, constant volume and isobaric specific heat. Same is true for water, any other material. These are properties of the matter. Okay? Well, what can you say about these two, the specific heats in liquids or even in solids? What can we say? Yes. They will be equal. But why is that the case? And we assume that they don't really, they are incompressible, right? So because of their incompressibility, I don't know, there is incompressibility. What's going to happen is that C of V and C of P for liquids, and I'm sorry for about the handwriting, guys. Solids is equal. We can actually prove this mathematically. So we have defined as enthalpy, which is a function of temperature and pressure in solid, right? Volume doesn't change here, so it is not really a function of volume. We have already defined this as also a function is equals to U, which is a function of temperature plus P divided by V. Right? Let's take the derivative of this with respect to temperature by keeping pressure constant. This is not a function of pressure, so it doesn't really matter. And then what will happen to this side? This part, volume, the idea is it's solid and liquid, so it is incompressible. Volume is constant, right? And pressure, we are keeping it constant. So that the derivative of a constant with respect to temperature, which is going to be 0, right? So for an incompressible liquid, the derivative of enthalpy with respect to P at constant temperature is equal to the derivative of U with respect to T. Since the volume is already constant, this itself is equal to derivative of U with respect to T by keeping volume constant. Which this was the definition of C of P, this was the definition of C of V. So isobaric heat capacity is equal to constant volume heat capacity, and for liquids and solid or any incompressible material. Is this clear? What about the ideal gas or gases in general? Gases in general are compressible. And in aerospace engineering, we are mainly flying, meaning that we are mainly dealing with gases, right? So we need to have a very good perspective on compressible fluids in general, or gases in general. So what can we say about CP, CV, all of the other properties when it comes to gases? The first thing we need to introduce here is the compressibility of a gas, or Z factor. Compress. I always have trouble with spelling this one. Compressibility of a gas, which is defined by Z. If I don't think you have, but if you have past fluid mechanics, in fluid mechanics we use a different notation for compressibility, but it's all the same thing, right? And we define the compressibility of a gas as P multiplied by V, pressure multiplied by volume, divided by R multiplied by T. Okay. You can also rewrite this using the universal values V bar and R bar, and if you call the universal gas constant is going to be 8.3.4 kilojoule per mole Kelvin, right? Which is more common in chemical engineering, but in mechanical and aerospace engineering we don't really deal with the universal gas constant that much. We usually deal with just the gas constant because, especially in aerospace, we are mainly dealing with air, right? We don't have that many materials present here. As long as we know just the gas constant of one material, we should be fine, right? So the first thing that comes into play when dealing with gases is the compressibility factor Z, which of course when Z is equals to 1, we are dealing with an incompressible gas, right? That's based on definition. When Z is equals to 1, we say we are dealing with an incompressible gas. Let's do that. Let's put Z equals to 1 and see what happens. So 1 equals to PV RT, and then we can say P equals PV, and this is a small v, this is just a specific volume, V divided by M, keep that in mind, equals to RT. What does this remind you of? The ideal gas law. So an ideal gas is an incompressible gas. Which doesn't really exist, right? Any questions so far? Who can tell me here what is a mole? Let's go around there. Yeah.
It's Avogadro's number. You said a mole, right?
Yes.
It's Avogadro's number.
So mole is a unit of measurement of amount of substance, right? And it's essentially 1 mole contains 1 Avogadro molecules, right? And what was the Avogadro number? 6.22 multiplied by 10 to the 23, right? Something like that, right? So this, as long as you have a bulk of 6.22 10 to the multiplied by 10 to the 23 molecules present, you have 1 mole of that substance. Okay? But we don't really use mole again. That's more for chemical engineers. Yes?
They're meaning to change that. They're trying to change the ampere, the mole, the Planck's constant, and the kilogram.
Okay. What do they want to do? And who's they here?
Huh?
Who's they?
The SI people.
SI people.
Because right now the kilogram is tied to a physical object that's in the basement of some building in France.
Yep.
And they're trying to move away from that.
They have already changed that, actually.
They already changed
Yeah, that's based on the 1 meter is based on how much light travels in a specific amount of time, how much photons travel. Yeah. But I'm not sure what they are going to do with mole, though.
Well, they're all tied together, so that's why. There's an equation that ties Planck's constant to Avogadro's number, Avogadro's constant. So now they're both constant, which means now the kilogram is allowed to fluctuate by the millions.
Okay.
So that's about it.
Yeah. I guess I can ask you to. Let's actually do this thing. Since you brought this up, why don't you prepare a 5-minute presentation on the changes they are making? Yeah, I mean, you can just present it to us next week, huh? What's that?
I got it from YouTube. It's a 5-minute video.
That's all right. Why don't you present it to us next week? Next Monday. Okay. That's an interesting topic. And I will of course give you a bonus point for this. Just okay. Let's see. So for ideal gas law, we said the equation of a state is, for an ideal gas, the equation of a state is PV equals to RT. Well, what is the equation of states for a regular gas? Does anyone have any ideas? PVZ equals, I guess that's a very good, yeah. No, that's true though. That's true. But it is the problem is here we are gonna have a lot of unknowns, right? So we need to be able to at least remove one of the unknowns here, right? There are many approximations actually that are going to give us. There are many different models, but I guess the most complete model is called the virial model. Virial equation of state, and this is essentially, it works by giving you some functions of pressure, temperature, B, C, D, whatever you want to call it. Doesn't really matter. and so on and so forth. So we have removed pressure from this equation, right, by using this. And all of the models of the equation of state that you are going to see are actually a representation of this model, some sort of a simplification of this specific model. You find the relationship between temperature and pressure, and using any method, you remove the pressure from your equation of state, and then you have the relationship between the volume, temperature, and the compressibility factor. Any questions? Okay. But we mostly are going to deal with the ideal gas law and the equation of state. Usually when we have some compressibility present in this course, it is usually given to you, so you essentially can use it as a correction factor in the equation of state. So you can actually use, what was your name? Drew, yeah. You can actually use what Drew said. You can use this in as a correction factor in your ideal gas law. So you don't really go, the equation of state is not a focus of this course, so you don't really need to deal with this. Let's go back to the ideal gas law and let's see what we can do to find some relationship between Cp and Cr for an incompressible gas or an incompressible solid or liquid. What we had was Cp is equals to Cv, right? That was for a solid and liquid. But it is not true. This is not true for an ideal gas though, right? Because gas doesn't really matter how much we assume its compressibility is 1, it is not going to be incompressible, right? So we need to come up with a different model. What can we do? Let's go back to the definitions we have. That we said enthalpy, internal energy can be defined. I'm sorry, just writing from my notes, and I have some problem with my notes here. Enthalpy can be defined as can be defined as internal energy plus PV. We are dealing with ideal gas, so your enthalpy and internal energy are only going to be a function of temperature. So that's actually very important to know. Ideal gas, enthalpy, and internal energy are only going to be a function of temperature. So when defining Cv, we have du dt with b constant. We can actually rewrite this as du as Cv dt. We can do the same thing for Cp, pressure constant. Then we can rewrite this as dH is equals to Cp dt. Make sure you remember this, because this is something you will use again and again and again and again for different so du is going to be the derivative of internal energy is Cv dt, and the derivative of enthalpy is Cp dt, which essentially means that for finding the delta U, the internal energy change between two different states, just have to take the integral between Cv dt, and to finding the delta H, you just have to take the integral between Cp dt. Right? What will happen to these equations if we assume Cv and Cp are not a function of temperature, which they are, but if we just make the assumption. And what will happen to the integral? No, it's just the integral of dt, delta t, right? So if constant, if Cp and Cv, not constant, not a function of temperature, not a function of temperature, then these equations become Cv delta T and Cp delta T. And this is actually an equation you have seen before, but for an extensive property, for Q, for the total amount of heat. Q equals to mc delta T, right? This is something we have already seen, at least a different form of it. Which one?
The two, like if Cp and Cv are not dependent on heat.
That's Cv delta T and Cp delta T. Because you can take Cv and Cp out of the integral, right?
Yeah.
And the integral of dt is going to be delta T. Okay, let's go back to the definition of delta T. dH is equal to du plus Pv. Right? What can we replace this with? You're dealing with an ideal gas, right? What is Pv equal to? RT, right? That's P. Okay, that's just keep in mind. We are always dealing with pressure and a specific volume. Maybe I should a specific volume, right? When you are dealing with a specific volume, ideal gas law is Pv equals to RT, right? And this is also the gas constant, not the universal gas constant. So the N doesn't really play a role in our calculation. That's the number. What is N? The number of moles. We don't really do moles here. Okay. So let's replace that. dH is equal to du plus RT, right? You want to ask what? Yeah. That's the idea. And let's take the derivative with respect to t. dH dt equals to du dt plus if you take the derivative of this with respect to t, you are going to end up with an R, right? This is the definition of Cp. This is the definition of Cv, which essentially means that for an ideal gas, Cp is equals to Cv plus the gas constant. That's the specific gas constant, yes. That's the, whenever, so it is either gas constant or universal gas constant. I don't really use a specific. Whenever I say gas constant, it's a specific gas constant. Any questions? So I think at this point we are ready for the second law of thermodynamics. Thermodynamics. Am I going too fast? I think so. A lot of you are still writing. Just have to let me know if I'm going too fast or too slow. I guess no one really has any problem with too slow, but too fast. Because if to be too slow, you can always go to sleep, right? That's the worst that can happen. Yeah, but I have to upload them, so you never know when that happens. And I'm a lazy person. Okay, second law of thermodynamics. Before doing the second law, let's remind everyone of what the first law was. What was the first law of thermodynamics?
Energy is conserved.
Energy is conserved, right? Which essentially in mathematical, if you want to represent it using mathematics or using, I guess, notations, the amount of change in the internal energy is going to be equals to the amount of heat input minus the amount of work done by the system, done on the system, whatever. Okay. Using this, can we have a system that takes heat from a heat source and use all of it to generate some work? Using this law, we can't. Yeah, yeah.
The second law says we can't.
And we are talking about the first law still, right? So Nick says we can, right, using this law. So essentially, if the amount of changes of your internal energy is 0, all of your heat is going to be converted to work, right? Is this true? Does everyone agree? No? You don't agree?
No, I do.
Okay. I guess this is not the sign of...
No, I know. I thought you were about to say something else than that. So.
Yeah, that's all right. Okay. And, but which is not something that happens in real life, right? So, you can see that the first law is not very complete. We need to be able to account for the things we call irreversibilities, right? Irreversibilities. Meaning that there will be some wastes in that conversion of heat to work. And ideally, we can really convert all of the heat to work. Some of the heat should be transformed to another heat source, right? Which you usually call QC. So based on this idea, we have 3 different statements when it comes to the second law of thermodynamics. First one is called the Clausius statement. Clausius states that it is impossible for any system to transfer heat from a cooler body. I don't want to write all of it. To transfer heat from a cooler body to a hotter body without any work. What is an example of transferring heat from a cooler body to a hotter body? Someone said something.
Getting a heater in the house.
A heater in your house.
Or, wait,
Refrigerators, yeah. What is that? What? Refrigerators? Okay. Yeah, refrigerators is a good example. There are millions of examples. I'm pretty sure if you think there are millions of examples. So the idea is, without any work, we cannot really remove heat from the refrigerator and put it into the room, because the refrigerator is by definition colder than your room, right? Which is something that makes sense to us, right? So Clausius statement. The second one is the Kelvin Planck statement. And Kelvin Planck statement says that it is impossible to operate any system in a thermodynamic cycle and deliver. I'm just going to read from the statement itself. And deliver a net amount of energy, by work, probably if I just read this better, to its surrounding while receiving energy by heat. Or by heat transfer from just a single reservoir. In other words, there is no way you can have a train. This train example is actually very famous. I don't know if you have ever heard about it, but there is no way that we can have a train that runs by making the environment around it colder. So by removing heat from the surrounding environment, right? This train example, that can't happen, right? And the last one is the entropy statement. Entropy statement, which essentially says, this one is the, I guess, most theoretical one. It is impossible for any system to operate in a way that entropy is destroyed, which is essentially means that it is impossible for delta S to be smaller than 0. So entropy of the second state cannot be lower than the entropy of the first state. The first state. Okay, yes.
So which one proves the heat death of the universe?
The heat death of the universe.
Yeah, which state?
What is the heat death of the universe?
Like inherently the universe will become cold because where there's order it turns to chaos. So,
Let me ask you this: what happens? What happens when universe dies? When universe, like when the heat death happens?
just runs out of heat.
What does it mean?
There's no more heat being generated.
No more heat being generated. I guess, I mean, it's let's actually talk about this. It's an interesting discussion, and encourage everyone to join in. What does heat mean? I guess go a little deeper. Movement of molecules. So when there is no heat, meaning when there is no energy, what happens? Molecules stop moving and colliding to each other, right? They are spread so much that there is no force between them that causes them to move. This expansion has happened. The universe has expanded so much that the molecules of the universe stop moving, right? There won't be any energy transfer. So the Big Bang's energy runs out, essentially. That's the idea. All of it goes to waste. So I guess which statement proves the heat death
You always hear whenever anybody talks about the heat death, like, because of the second law of thermodynamics,
Yeah, so that's, I mean, I'm thinking all of them can actually prove that, essentially, because when you are moving, you are transforming your energy, internal energy, to work, right, when the molecule is moving, right? And because of the waste that has to be present, you're losing the energy, the amount of energy during this transformation, right, between one molecule to another one, right? So I assume all three can point to the heat death. Do we have anyone else who wants to talk about this, or has an opinion on this, or has some information that can, like,
a lot of it being transformed, like basically stores go into making atoms that are apparently bigger and cooler. Like, that's why I see most of go into making atoms that are smaller in a small stage.
my knowledge of astrophysics is very limited, so whatever I say is going to be my opinion after this, not something that I really know about. But let's stop here if there's no one else. Let's continue the second law when it comes, from an aerospace and mechanical engineering perspective, and we'll go on from there. We usually use the Kelvin Planck statement because we deal with cycles. Yes. We will talk about the isentropic. What was the? Can you repeat what you said? Are you talking about simplifying the heat death of the universe, or like in general? Yeah, sure. The isentropic. Yeah, definitely. So can you tell me what is the isentropic process? What is isentropic process? Entropy is equal to 0, or the changes in entropy. Changes in entropy is equal to 0. Yeah, that's one part of it, right? That's essentially the reversible part of isentropic process. What is the other part of an isentropic process? Anyone else? So we have different processes, right? We have in thermodynamics, and that's a good segment that we need to talk about. We have constant volume processes, right, in which the volume remains constant between state 1 and state 2. We have constant pressure processes in which the pressure remains constant between the state 1 and state 2. We also have reversible processes in which the entropy stays constant between state 1 and state 2, right? The other type of processes we have is adiabatic processes. What is an adiabatic process?
zero work is done on the system, right?
Zero work? Anyone else? What does it have to do with heat? No heat transfer, right? So heat is 0, not work. No heat transfer throughout the process from 1 to 2. So Q1 to 2 is 0, right? Adiabatic process. And we also have isothermal process in which the temperature remains constant. T1 equals to T2. But we also have isentropic processes, which are this doesn't really happen in real life, but this is a very common assumption. That's essentially the ideal type of process when it comes to turbines and pumps, right? So what is an isentropic process? One part of it is that it is a reversible process. right? So entropy doesn't change. What is the other part of it? What is the second part of an isentropic process? Does anyone remember? The process has to be adiabatic. So we actually can call this adiabatic reversible. So essentially the entropy statement of the second law tells us that we can have a reversible process in theory, right? We can have a reversible process, but it doesn't really happen because of the efficiency limitation. So based on this discussions, based on the second law discussion, any cycle, any conversion of work to heat will have an efficiency. I mean, it is efficient to some degree. We can transform some part of work to heat, some part of heat to work, right? Some other part of it won't transform to heat. So based on, let's use the Kelvin Planck statement, which refers to cycles, right? Essentially tells us that there is a thermal reservoir with QH that is giving heat to a system. The system is working on the surrounding, and the rest of it, heat goes to a cold reservoir. Hot reservoir. Cold reservoir. Okay, and the efficiency, the idea was we cannot convert all of this QH to W, right? That's the idea. So we define the efficiency of a cycle as the work of the cycle divided by the amount of heat input. And this is defined for a reversible power cycle. And keep in mind that these cycles are called power cycles because we are essentially converting heat to power. And we're going to see later on, like in Rankine cycle, we have a boiler. We are heating water or whatever, usually water, and it changes its phase to vapor, and we put that vapor in a turbine. That turbine transforms that heat to work, right? The shafts start moving and usually connected to a generator that generates electricity, and so on and so forth, right? Also in this type of cycle, W of cycle is equals to QH minus QC. So we can rewrite this efficiency as 1 minus QH divided by QC. There is in the PowerPoints that I've uploaded, there is a small discussion on what is entropy that we are not going to go into today, but it is nice to look at it. If you have the time, just go and read it and see what it has to say. Of course, as is true for any engineering courses, we are really interested in formulating entropy. How can we calculate entropy of a system, or how can we calculate the changes in entropy? We essentially define entropy using the Clausius inequality. That says the integral of partial Q divided by T at a boundary of the system is always smaller than 0. Okay, And this integral is actually the changes of entropy, negative of the changes of entropy. This essentially refers to the amount of heat that passes through one boundary of the cycle, right, at a specific temperature. Changes in that heat at a specific temperature is always going to be smaller than or equal to 0. So, based on this, if this is smaller than 0, negative delta S is smaller than 0, delta S is going to be larger than 0, which refers to an irreversible process. Is negative delta S. If negative delta S is equals to 0, then delta S is also equals to 0, which refers to a reversible process. But can we have this? Based on this inequality, we can't have negative delta S larger than 0, because then this inequality won't be true anymore, right? This essentially means that entropy is destroyed, right? Entropy between two states, at the second state is going to be smaller, or delta S is smaller than 0. This is impossible based on the second law. So reversible irreversible and impossible. But the question is, so based on the second law, we cannot convert all of the heat to work, right? Well, what is the maximum that we can achieve? What is the maximum amount of heat we can convert to work? This is an ideal case that is defined by a Carnot cycle. Carnot was a French guy, so it is written as Carnot. It is pronounced Carnot. Are you familiar with Carnot cycle? A little bit. So can you tell me that little bit? No. That's alright. Is there anyone else who can talk about Carnot cycle a little bit? Yes.
Looks like it's close to get to perpetual residue change, or that?
Sure.
It's most amount of heat turned into work. So like Stirling engine, like the Carnot cycle.
That's the most amount of heat you can turn. That's the definition of the Carnot cycle. That's the most amount of heat you can turn into work, right? But the perpetual motion machine refers to no waste, right? So I don't know if that's, can you, what's that? What would it, so if they end up inventing a perpetual motion machine, what does it mean? What does it mean for the second law? So that's, we are one step actually before the Carnot cycle. We have already agreed the second law exists, right? Best what? Best engine. I'm not sure about the number, but like if you are dealing with a power plant, it's usually around 40% the Carnot cycle efficiency. If you are talking about the ICEs, internal combustion engine, is closer to like 70-80%. It really depends on the engine, right? But I mean, so essentially for any cycle, you can calculate the Carnot efficiency of that cycle, right? And that Carnot efficiency is the maximum you can achieve based on the temperature of the hot reservoir and the cold reservoir. So they tell you that this is the temperature of the hot reservoir I have, This is the temperature of the cold reservoir. Based on the only the two temperatures, you can find the maximum efficiency you can achieve for a reversible process. Okay, and like Carnot cycle, let me see. The efficiency of a Carnot cycle is usually 1 minus Tc divided by Th. It is not on my notes, so make sure to, for whatever reason I don't have this efficiency on my notes, but make sure you write this down. So efficiency of a Carnot cycle, 1 minus Tc to Th. So that's the maximum efficiency we can achieve. And PV let's actually draw the PV diagram for the Carnot cycle. If you are dealing with a piston, a PV diagram of a gas power cycle essentially is going to look like this for a Carnot cycle. That we go from 1 to 2, then to 1, 2, 3, 4, right? This is going to be your Tc, this is going to be your Th. So the ratio between these two is going to be equal to your Carnot cycle. But for the Rankine cycle, this is for a gas power cycle, like an ICE engine or a jet engine. But for the vapor, we will talk about this in the next lecture a little more. Vapor cycle, your PV is going to be looking like this. If you don't remember this from your thermodynamics studies, are right. We will definitely talk about this later. Talk about this in like 5 minutes. The last thing I want to talk about in this thermodynamics review is the TDS equations, or the entropy equations. We were going toward that way. We saw this inequality. So your delta S is actually, between the two states, is actually equal to integral of del Q divided by T for an internally reversible process. Did anyone knock on the door? There's all these sounds coming in. Chalkboard on the side. Yeah, that makes sense. That makes a lot of sense. So, and if we are not dealing with an internally reversible process, we only need to add a correction factor here. Correction factor sigma. That relates to the irreversibility of the system, right? But the Q, delta Q internally reversible itself, based on the first law, is equal to changes in the internal energy, right? So the amount of heat added to a system during an internally reversible process is equal to the change of internal energy plus the changes of the amount of work done on the system during an internally reversible process. Let me ask you one question though. Why did we replace U? Did you replace E with U? It was dE, right? At the beginning, the definition of, but it is not dE anymore. dE refers to the changes of total energy of the system, and as I said, we usually ignore the kinetic energy as well as the potential energy, right? So the only thing that is left is the internal energy. Well, based on the definition, we already have seen this in the previous lecture, that del W is equal to PdV, changes in volume, and del Q for an internally reversible process is equals to TdS, right, from this definition. This definition, right? That's don't forget this in exam at every step. So we said del Qt equals to S, right? That was the idea. Equals to ds. I'm sorry. We have just moved t to the other side. Okay, so if you replace these into these equations, TdS is going to be equal to TdU plus PdV, and we are going to use the intensive properties here. Let's use the definition of dH. We said dH is equals to U plus, so we said H equals to U plus PV, right? So dH is equals to du dPV. Okay, how can I expand this? It's going to be, it's a just chain derivative, right? It's going to be PdV plus VdP, right? Is this clear? Yes? Okay. So let's replace, let's put that here. dH is equals to du plus PdV plus VdP. And we can actually see that these two are the same. So we can replace this with TdS. So dH is equals to TdS plus VdP, or we can rewrite it as TdS equals to dH minus VdP. And we had the original equation as this. These two are the most famous entropy related equations out there, right? TdS equations. And whenever you are dealing with entropy or cycles, you will eventually see these equations somewhere. Even when you are dealing with like compressible fluid flow, like shock waves, you will see these equations. So it is not a bad idea to just, I guess, memorize them. I mean, learn them. Okay. What will happen to this equation if we are dealing with a solid or a liquid? What will happen to the calculations of ds? So let's actually, for the solid or liquid, let's move t to the other side for both equations. ds is going to be dH dt minus VdP, right? Also ds equals to, this is du, I'm sorry guys, make sure this, you are using the correct. This is du dt plus P dV. So for solid or liquid incompressible substance, dV is 0, so this part is 0, right? There is no changes in volume. And what is du dt? That's CV. But for a constant volume, for a constant volume case, right? Zero. Just let's keep this keep it like this, right? What can we say about this? ds equals to dH minus vdp. I made a small mistake here. That's why I get my mistake. So TDS is equal to this. That was the equation. This part is 0, and then ds is equal to du over t, right? Or we can use this equation. So du, based on what actually Lawson said, we already know du dt is equals to Cv for an incompressible gas, right? This is always the case for an incompressible gas. It is always V. It is not 0 though. The second statement was not correct, right? So, pardon me?
I was just saying stuff and seeing what works.
Yeah, what is stuck, huh?
Yeah.
That's a good plan. So ds is going to be equal to C dt divided by T for an incompressible substance. Can we take the integral here? If you take the integral from the left hand side, you're going to have S2 minus S1. Then the integral of C dt T. If we assume C is not a function of t, then we'll end up with a 0, 1 to 2 dt divided by t. And what is the solution to this integral? Natural log of t2 over. So for a constant c, s2 minus s1 for solid or liquid, S2 minus S1 is going to be equal to C natural log of T2 divided by T1. Well, what can we do for an ideal gas? Let's go back to these original equations. Let's actually finish this, and or we can finish this next week. Let's stop here. Yeah, let's stop here, and we're gonna continue next week. Next week we are going to talk about the power cycles. Hopefully we can finish the review of thermodynamics next week, and we'll move on to the meat of the discussion.